Okay, so last time we had defined, okay, so we already know that we have this thing W, if you have a word, then you can send it to PW, right? And this can be achieved using Knuth moves. So this means that there is a sequence of Knuth moves. What were the Knuth moves? Let's see if I remember what they were. X less than or equal to y less than z, then we have so y is in the back for this, or I know it's on the end. Which end is the question? If it's wrong, we'll know soon enough. So yeah. So these are Knuth moves. So we saw that using Knuth moves we can achieve this, and I guess you solved during the tutorial the exercise also about the syntactic monoid, that if two things are Knuth equivalent, then the operators that insertion gives rise to will be the same. And what we so this implies that if PW is equal to PW prime, then W is congruent to W prime, because W is congruent to PW, PW prime is congruent to W prime, so W is congruent to W prime. So what we want to do is prove the converse, that if W is congruent to W prime, then PW is equal to PW. Yeah. In other words, what we are trying to say is that, so these equivalence classes are called plactic classes, okay, and the plactic monoid PL(an) star is defined as the monoid (an) star modulo this equivalence. Because this equivalence is a rewriting rule, it descends to the monoid structure descends to the equivalence classes. So what you need to check is that if W1 is equivalent to W1 prime and W2 is equivalent to W2 prime, then W1 W2 is equivalent to W1 prime W2 prime, and that's because of the nature of this equivalence. So this is called the plactic monoid, and these equivalence classes are called plactic classes. So what we want to show is that if W is congruent to W prime, then PW is equal to PW prime, which means essentially that so P of a tableau is the same tableau itself, right? If I start with a word that's a tableau and I take its insertion tableau, I get that same word, nothing happens. So what we are trying to say is that each plactic class contains a unique tableau. So this is equivalent to saying that if two tableaux are equivalent, then they are equal. Right, because if W is congruent to W prime, we know that PW is congruent to PW prime, and we want to show that they are equal. So this is what we want to show. So the proof of this uses something else which is called Green's theorem, and along the way we will also see so this tells us what is the shape, interpretation of shape. Let us not forget we have Pw and we also have P star W. So, of the shapes of Pw and P star W. So, Green's theorem gives an interpretation of this, and it also gives rise to a very beautiful duality theorem. So, we will see all this today. This equivalent to this? Okay. So, firstly, suppose we know this, right? Then if we know that W is congruent to W prime, then we know that Pw is congruent to Pw prime. So, this implies this. If Pw is congruent to Pw prime, then W is congruent to Pw and W prime is congruent to Pw prime. So, Pw is congruent to, so W is congruent to W prime. So, these hypotheses are equivalent, the conclusions are the same. So, we will talk about green invariants. So, remember a row subword is a weakly increasing subword, right. So, if you have a word W, then a row subword is AI1 AIR, where I1 less than I2 less than IR and AI1 less than or equal to AI2 less than or equal to AIR. That is a row subword. And similarly, you have column subword, where you have I1 less than I2 less than IR, but AI1 strictly greater than AI2 strictly greater than AIR. And we will say that two subwords are disjoint if the indices, the letters that they pick are disjoint. Okay, not that the values are disjoint, the positions from which they pick them are disjoint. So, subwords, so AI1, AIR and AJ1, AJS are disjoint if the subsets I1, IR and J1, JS are disjoint. Okay, so with these in mind, I am ready to define green invariants. So, AK, maybe not AK, alpha K W is defined to be the maximum total length of a union of K disjoint row subwords. And beta KW is defined to be the maximum total length of a union of K disjoint column subwords. Okay, so let us look at an example. So let us look at this word 325146. Oh, right. Or maybe let's look at a better example. This one has all distinct letters. Okay, anyway, let's look at this. So what, maybe it's better to look at something without distinct letters. Here's one that I have, nice one. 3, 4, 4, 2, 3, 3, 1, 1, 2, 3. Okay, so let's look at this word. And what is A alpha 1 of W? So you know that if you want to compute alpha 1 of W, Schoenstedt already told us how to do this. He said, well, just start inserting these things into a row, some things get thrown out, the length of that final thing that you get, the first row, that's A1, right. But this guy, if you start inserting, you will very quickly notice that it's already a tableau word, right. So it's like this, 1, 1, 2, 3, 2, 3, 3 and 3, 4, 4. Now when it's a tableau word, you are already given a subword of length 4 over here, right. You are reading it like this, 3, 4, 4, 2, 3, 3, 1. So you have a subword of length 4. Can you do any better? Okay, so suppose you had a row subword, then you would choose, suppose you chose an element of, suppose I started with 2 and I want to look at a row subword that contains this 2. Okay, so after this what can I do? I can only use the elements to its right. I cannot use any elements in this particular column. Okay, here if I start with this, then maybe I can use this element because it comes later, provided it is, no, but it would be less. So I can't use anything in this column. So basically, once I use up something in a column, I cannot use anything else in that column. So an increasing subword can have at most one element in each column, provided the word I started with was a tableau. Okay, so I cannot have like more than one word from each column. So the longest possible word I can have would have length 2, because at most there are anyway 4 columns in here, right. So here the alpha 1 W is 4, alpha 2 W. So the same principle now applies if I want to find 2 words. Each word would have at most one element from each column. So maybe the first word I would pick 1, 1, 3, 3, and the second word I would pick 2, 3, 4. But now I have 2 words, so I have picked at most 2 elements from each column. So if I just sort of float them up, then I will have occupied the elements of the first 2 columns. So if I have 2 disjoint subwords, it would be so I cannot get more than 7, but I can get 7 exactly by taking these 2 subwords. And alpha 3 W, well, the whole thing is a union of 3 subwords, so it's 10. So at least for a tableau word, it is very easy to calculate the green invariants, because the word is already given to you in a nice form. We will just compute beta also here in this case. So let's see. So yeah. Huh? Because okay, alpha 2 is 7 because okay. So firstly, it's less than or equal to 7. It can be 8. No, it has to be less than or equal to 7, because totally each word will have at most one letter from each column.
In this word, if I take 3, 4, 2, 3, 1, 1, 2, 3.
3, 4, 2, 3, 1, 1. But how is 2, 3, 1, 1, 2, 3 a row subword?
Because of this.
Yeah, but then 2, 3, 1, 1, 2, 3 is not a row subword.
No, 2, 3 only is a 2-letter
Uh-huh.
subword.
Alpha 2 means at most 2 2 disjoint subwords. Okay, so alpha 1 is the length longest row subword, alpha 2 means I must take 2 row subwords and the maximum total length. Okay, so I can take one of length 3 and one of length 4, so it's 7. What about beta? So what is the longest? So if I use now, yeah, let's just. So if I take a column subword, right, I can only use one element in each row because the rows are weakly increasing, I want strictly decreasing. So once I use up an element of one row, I cannot use any more elements in that row. So you see, it's the other way around. It's and now if I have 2 column subwords, they would use up at most 2 elements of each row. So it's the sum of the 2 longest rows, 6 and 9. Here alpha 4w is also 10. Okay, it doesn't change anymore. I've used up all the letters. So this is the calculation of alpha and beta for a tableau. You can also do it for dual tableau. You will get the same answers. So if the shape of the tableau is, so what we are saying is that if W is, so what we are, if W is a tableau of shape lambda, then alpha k W equals lambda 1 plus lambda k, the sum of the first k rows of lambda, and beta k W is the sum of the first k columns of lambda. Usually that is denoted by lambda 1 prime k plus lambda prime k. So these are column lengths or the parts of the conjugate partition.
For a tableau word, the disjoint sequences that you consider are exactly rows.
They can be, yeah. The rows will give you that, yeah. I just proved it.
In general, it's not true that
For a tableau word, it's true, right? I mean, clearly the rows give the right size, and you can't do better than that size because of this argument that you can choose at most one letter from each row and each column. So yeah, so that's one interesting point. The other interesting point is, so maybe we can call this a lemma, though I didn't prove it, I only gave an example, but you can easily generalize whatever I said, that each row subword contains at most one element from each column, and each column subword contains at most one element from each row, and using that you can show this. The other thing which is a little more interesting is, if W is congruent to W prime, then alpha k W for all k. Now suppose we knew both these things, then if we start with the general word, that gives us a nice algorithm. We have a nice algorithm to compute alpha k and beta k. What do? You start with your word, then using Knuth equivalence, you can turn it into a tableau word, and then just by looking at the tableau word, you can read off alpha k and beta k. Right. So, together these two things give us the would give us what is called Green's theorem. And the thing here is that somehow Knuth equivalence is defined in terms of two relations which are simple enough. So, to prove this, we will just prove that if W and W prime differ by a single Knuth move, then their alpha k's and beta k's are the same. So, the point is that these Knuth moves are simple enough so that you can verify that, and yet they are general enough so that you can go from a word to its tableau. So, let us prove this lemma. It is a simple but elegant proof. So, it is enough to prove it for W and W prime differing by a single Knuth move. So, we can I do not remember which I called K1 and which I called K2 last time, but so we will take one of these and prove it. The other proof is quite similar. So, let us take for example K1. So, what we have is W is of the form U x z y and W prime is of the form U z v and U z x y v. That is what it means to differ by a Knuth move. These are not letters, these are now words. So, you have a word U, then you have this x, z, y, and then you have a word v, concat. And so, this is what it means to differ by a single Knuth move, and of course, we must assume here that x is less than or equal to y is less than z. So, now notice that if you have a row subword here, it cannot include both z and x, because according to this z is strictly greater than x, right. So, it is definitely already a row subword of this, because it will either use z or it will use x, it cannot use both. So, it is still a row subword here, right. So, every row subword of W prime cannot have both z and x. By saying that it does not have both z and x, I do not mean the symbols, the letters z and x. What I mean is this element from here, the point in this position and the point in that position. You could have the same symbol occurring somewhere else. So, it is also a row subword. Of W, because the only thing that has changed is this xz has become zx. So, if they both occurred, I would not get a row subword, they would be transposed. So, what this says is that W has more row subwords than W prime. So, this means that alpha k W is greater than or equal to alpha k W prime for every k. So far so good, but the other thing seems to be a bit of a problem, right. What if you have a row subword here and it involves xz, then it would no longer be a row subword here, right? But maybe we could construct a different, this camera guy is not here, I mean he should be attending. Sound, please check the sound. So there is that potential problem, but maybe we could find a different row subword. For example, if we had, so if W is of the, so a row subword, so we want to show that a row subword of W, a row subword of W may not be a row subword of W prime, but maybe we can construct a different row subword. So suppose we have a row subword of W of the form, W1 equals U1 X Z V1, right? Then we could change it to U1 X Y V1. This would still be a row subword, won't it? Because X is less than or equal to Y and Y is strictly less than Z. So whatever order you have, Z is less than or equal to the first letter of V1, Y will also be less than the first letter of V1. So this would be good, but the problem is we are using up one letter which was not used earlier. So if we have other subwords, then this would cause a problem, right? So let's just say that, but we'll use this idea nevertheless. So suppose we have W1, W2, Wk, row subwords of W, and if none of them involve xz, then we are fine, right? But let's suppose one of them involves xz. So let's assume W1 involves xz, whichever involves xz, we'll call it W1. U1 xzv. Now if none of W2 up to Wk involves y, then we are fine. Then W1 prime equals U1 xy V1 W2 Wk are row subwords of W prime, are disjoint row subwords of W prime. And they have the same total length. So far so good, but now the problem is, what if one of these other words involves y? If W2 involves, so only one of them would involve y. So let's say W2 is of the form U2 y V2. Then what do we do? And so this is the clever part. So what you do is, you say W1 prime, okay, if I do this, then I'll get into trouble, right? Because then what do I do with W2? So the trick is to take U1 of W prime of same total length. So that I think completes the proof for the Knuth move K1, and for the invariant alpha K. So now you have 4 more things to do, 3 more things to do, that is Knuth move K2, and then you have to do each one for alpha K and beta K. But I would just like to pause here for digression. There is this beautiful involution on the plactic monoid which is called the Schützenberger involution. So firstly, you can think of it as a involution on an star itself. So it's an involution which is usually, which I denote by sharp, from an star to an star. And what does it do? So if you take a word A1, A2, AK, then its hash is defined to be n minus AK plus 1. So this n minus I goes to n minus I plus 1. If I take I equals 1, then I'll get n, I equals 2, I'll get n minus 1. So what it's doing is, it's reversing the order of the alphabet. But I will also reverse the order in which the letters appear. So I'm making two reversals. So I'm reversing the order of the letters and the order of the alphabet. So this is called the Schützenberger involution. Wait, huh? Yeah. So so let's take n equals 4, and let's take the word 3, 1, 2, 4, 1, 2. So then I'll do it in 2 steps. First I'll reverse the order of the things. So reverse order of letters. That means I'll just read the word from right to left, and then reverse the letters themselves. And so, so what is that? So I have 3 letters, 1, 2, 3, 4. These become 4, 3, 2, 1. So whenever I see 1, I put 4. Whenever I see 2, I put 3, and so on. So this becomes 3, 4, 1. 2 is 3. 1 is 4, and 3 is 2. So this is 3, 1, 2, 4, 1, 2 hash is 3, 4, 1, 3, 4, 2. Now, interesting observation immediately is that if I had a row subword of W, I could construct from that a row subword of W hash. How? So let's take a row subword here. So let's take this row subword 1, 2, 2. When I reverse the letters, it becomes a weakly decreasing subword. But now what I am doing is, I am reversing the order of the alphabet. So again it becomes a weakly increasing subword, 3, 3, 4. Okay, so clearly the green invariants are in fact the same for a word, and so alpha k W is alpha k W sharp, and it's also true for beta k. What about the Knuth relation? So suppose I have two words which differ by a Knuth relation. What can we say about their Schutzenberger involutes? So I erased my Knuth relations. I should write them down in the corner somewhere and keep them. So so x z y z x y. What is the condition here? And yxz is congruent to yzx, and let's try not to erase this. So this is called K1 and this is called K2. So what happens if we apply Schutzenberger involution to K1? So, so I guess I can erase this board, right? I want to be close to the relations. So somehow the lights went off when I did the most crucial step in this proof. So it would be, for those who are watching, it would be, they can try to, the clever step in that proof. Okay, so let's take this. So let's call it K1 hash. So what happens to K1 under the Schutzenberger involution? So firstly, this condition x, y less than z will become, so maybe I'll call the new letter z prime, y prime and x prime. It will become z prime less than y prime less than or equal to x prime. This is n minus, so let's say I prime is n minus I plus 1. So this is what happens, right? So this inequality becomes this inequality. And what happens to this thing? So I'm looking at x z y is equivalent to z x y, and now I reverse the order, and so I get y z x is y x z, and then I reverse the letters, and so I get y prime z prime x prime is y prime x prime z prime. And now let me just let's substitute. Let's call this x, let's call this y, and let's call this z. So I get y, so setting x equals z prime, y equals y prime, and z equals x prime. This becomes y x z is congruent to y z x, and the condition has become this. So K1 hash is equal to K2 and K2 hash is equal to K1. So I don't really need to check the other Knuth relation. I can just apply Schutzenberger involution. Note the fact that the Schutzenberger involution does not change the green invariants, and of course it may have been easier to just prove the other thing in the first place, but yeah, this becomes K2. No, but then the inequalities are different, right? This has become this, but these inequalities are different, so they are not. So so this is a very good point you brought up, in fact. So you can talk about the opposite Knuth relations, or sometimes they call the dual Knuth relations, where you change these inequalities, flip the inequalities. But that is not, so the resulting quotient monoid that you get is not isomorphic to the plactic monoid, it is isomorphic to the opposite of the plactic monoid, which is easy to see. So it's just that you have the same elements, but the binary relation, the multiplication, the order is changed. So the so there's there's
Is that equivalent to saying that the Q's are same?
no, it's something else. Yeah.
You have shown that K1 implies alpha. That's what you have proved.
I have proved that if two words differ by K1, then their alphas are the same. Yeah. Then it says that if two words differ by K2, then also their alphas are the same.
Have you proved that?
No, but I claim it follows from the fact that K1 sharp is K2.
So basically you are saying applying this all four.
No, two of them for the alphas. For the betas, again, you need to do the same thing. Yeah. So now suppose I have, I mean, of course it's very easy to just take K2 and repeat the same argument, but I don't want to do that, right, for whatever reason. So what I'll say is, suppose W1, W differs from W prime by K2, then that means that W hash differs from W prime hash by K1, right? No, by K2 hash, which is K1. and so that, right, this is equivalent. This implies that alpha K W hash is equal to alpha K W prime hash. But as I explained to you, alpha K of W is the same as alpha K of W hash. Now for betas you have to do the same kind of argument. It's very similar in the sense that the same kind of steps come up, and the clever step is more or less the same. Okay, maybe I should anyway. So that's. So this Schutzenberger involution, another point that we have here is that an star to an star, we have the Schutzenberger involution, and then we have this map equivalence relations, and the fact that K1 and K2 interchange under the Schutzenberger involution means that if two words are Knuth equivalent over here, they are also their Schutzenberger involutes are Knuth equivalent, right? So that means that the Schutzenberger involution descends to an involution of the plactic monoid. So this plactic monoid has a symmetry which is the Schutzenberger involution. I will come back to this later. So, what we know is that every class in the plactic monoid contains a tableau. We are going to show that it contains a unique tableau. Also, we know that every class contains a unique contains a dual tableau. We will show it contains a unique dual tableau. So anyway, have we proved Green's theorem? Coming back to where we were a little while ago, we have, right? We have proved Green's theorem, as I explained. Proof of Green's theorem. So I didn't state Green's theorem, right? So alpha is the sum of the first k is the sum of the first k parts of the partition lambda, where lambda 1 to lambda L is the shape of PW, and beta KW is equal to lambda 1 prime plus lambda k prime, where these are the columns of the shape of PW, the conjugate. So let us say this is lambda, the same shape. So this is a corollary of this is that for every word, the alpha k's and beta k's are related by this fact. So if I know that I have a word whose longest increasing subword is longest row subword is of length 2, and the second longest is of length 3, and say the second longest this is the sum of two longest disjoint ones is 3 and this thing, then I know that if I take column subwords, then I will get the conjugate. Well, this one is self conjugate, so maybe I will add one more here. Four, 3, 2. So this is called Green's duality theorem, right? So this so in some sense this gives the explanation of the remaining rows in Shensted's insertion algorithm, and this is a very interesting duality theorem relating, says that the lengths, there is no reason a priori why the lengths of row subwords should be related to lengths of column subwords, right? But this is the amazing thing. So so I don't know if you have seen Dilworth's theorem. If you are into combinatorics, there is a thing called Dilworth's theorem. So it says that if you have a partially ordered set, then the cardinality of the largest anti-chain inside it is equal to the maximum number of disjoint chains that I can find in the. So this is in that same realm of ideas. There is a paper of Green and Kleitman where they talk about these things in the more general context of partially ordered sets. But here this, let us just look at it like this. And have we proved Green's theorem? Well, maybe I will just summarize the argument now. Why? Because W is congruent to PW and Knuth moves preserve green invariants. That's it. Okay, so now let's come back to this. Oh yeah, there's one more thing I want to talk about, which is what happens when you. So you have this map from an star when you remove a letter from your alphabet to an minus 1 star. So what I'm doing is I'm just removing the last letter from my alphabet. So wherever that occurs, so this is obtained from W by deleting all occurrences of n. So whenever n appears, you just delete it. Okay, now I have this map from here to the plactic monoid of an, and I have a map from here to the plactic monoid of an minus 1. The question is, will this descend to a map on the level of plactic monoids? So basically what I am asking is, if I take something which, if two words are equivalent here, I delete the last letter from both of them, will they be equivalent here, Knuth equivalent here? So for that we just again take a look at the Knuth relations. So the only issue would be if Z is equal to n, right? Z is the largest thing in each of them. So what happens if we delete Z from these Knuth relations? I get xy is xy, yx is yx. So clearly this last letter deletion descends to the level of plactic monoid. And let us see what happens to P of W under this. So, so maybe it's good to do an example here. So let us look at
In words, summarize so what you showed just now, you showed this was that two things were Knuth equivalent, that alphas will be equal to the same.
correct. So now W is Knuth equivalent to PW. That was the proof. So we proved that PW can be obtained by from W by a series of Knuth moves, and the proof of that was, you analyze row insertion, and whatever is being inserted can be moved up to the point where it gets inserted by one type of Knuth move, and then whatever was there can be moved out to the front. Yeah, it involves that analysis. So the proof does involve that analysis. And so that means that W is congruent to PW. And then we proved that alpha k is preserved under Knuth. So alpha k of W is alpha k of PW. Then there was a separate argument to show that if a word is the reading word of a tableau, then Green's theorem holds for that. That was easier. This clip is not. Yes. Huh?
For all like
Well, no, actually. Z, y x and y z are not Knuth equivalent. Yeah, there you go. Good question. Oh yeah, here's another thing I wanted to say, and this you can try as an exercise. Not that easy, but doable. It's a comment in one of Schutzenberger's papers that is another characterization. So we have had a couple of characterizations of Knuth equivalence. One is that they differ by a sequence of Knuth moves. That's what we took as the definition. The other is that their syntactic what is the word? They are syntactically equivalent as operators. It's not enough that okay, of course, W is congruent to W prime if PW is congruent to, but we need to prove if and only if. Okay, but W is congruent to P if their insertion tableau are the same. Here's another characterization purely in terms of Green's invariants. So, so first exercise is, if you have W congruent to W prime, no. So this one is easy. If alpha kW is equal to alpha kW prime, and even assume that weight of W is weight of W prime, does that imply that W is congruent to W prime? So I have two words with the same letters occurring in them, and their Green invariants. You could also work with beta. Then does that mean that they are Knuth equivalent? But here's a very beautiful characterization of Knuth equivalence. So W is congruent to W prime if and only if for all U V in A, for all K. Yeah, so 1, 2, 3 and 1, 3, 2. Oh, okay. Yeah. Yeah. So these are not Knuth equivalent. Okay, so you solved the first exercise. Spoiler here. Okay, so too late. So, but this is really beautiful. If for every U and V in A n star, alpha k of U W V is equal to alpha k of U W prime V, which is also equivalent to for all U and V in A n star. So let's assume these are in A n. So, in some sense, Knuth equivalence is determined by Green invariants, but not just on the words, on all extensions of the words. One way is easy, right? If for all K, of course. If W is Knuth equivalent to W prime, then UWV is Knuth equivalent to UW prime V, and so alpha k of UWV is equal to alpha k of UW prime V. But the converse is harder. So obviously you need this U and V, as the first exercise explains, that just because the Green invariants are the same doesn't mean that they are Knuth equivalent. Sorry? No, I am not assuming anything now.
The weights are the same.
No, I am not assuming that here. Here you would say, okay, so here you could also not ask for that, but then it's too obvious that they are not Knuth equivalent, right? But here you don't need to assume that the weights are the same. That's maybe not so surprising because you're allowed to add things, so you know. So you don't need to assume anything, it's exactly as stated. So that's a very interesting exercise because what you have to do is now you have to construct some u's and v's which will distinguish between non-equivalent words. But maybe it's easier to solve this exercise after I finish today's lecture, but anyway, it's a good point to give the exercise. So, yeah, I don't know that Knuth equivalence is characterized by the Schutzenberger. I mean, that's too, yeah. There are probably several equivalences. Any equivalence which is symmetric under this. I mean, okay, some stupid answer to your question is take no equivalence, right? But, so what do you mean exactly? That's a very good question. I think you only need one of them for each of the things. If I remembered my proof correctly. So there is just a comment in one of Schutzenberger's papers. Maybe the proof is there in another of his papers. I don't know, but I had to only construct things on one side, I think. I'm not sure, so I can look at my notes and see. Okay, so now I want to prove that oh yeah, no, there's other thing, yeah. So here's another lemma. So we have this W goes to W bar, and I want to say that P of W bar is P of W bar. Okay, so let me just do an example here and show you what this means. So let's take one of these many examples of So P of W is also a word. I'll delete all occurrences of n in it. So in terms of tableau, what I'm doing is whenever n appears in that tableau, I'll just remove that box entirely. Right, so suppose I take a word like 3 1 2 2 1 3 1 3 and W bar is 1 2 2 1 1. Let's take n equals 3. Right, so let's just compute P of W. So P of W, first the 1 pushes down the 3 and then we get 2 2 and then this 1 pushes down the 2 to the 3 and then the 3 comes here and then this 1 pushes down the 2 here and then I have this 3. That's it, right? I hope I did it correctly. I'll soon know. So 1 2 2 and then the 1 pushes down the thing. So I get. So this is what is left after I erase these 3. Right, and the reason for this is it's not very difficult. The point is when I insert a 1 or a 2, the 3 doesn't really, you know, interact with them. They don't see the 3 really. If it cannot come to rest, it can bump up a 3, but if the 3 wasn't there, it would just come to rest in the same place without bumping up the 3. Like for example, I had this 3 bumped up, right? At what stage was this 3 bumped up? This 3 was first bumped up when I put this 1 in, right? So then I had this 1 and then this 3 got bumped up here. Yeah, this. Huh? 2, 2, 3, is it? It still works. Okay, so when the 3 gets bumped up, okay, it gets bumped up, but if the 3 wasn't there also, this 1 would have come to rest in exactly the same place. So as far as the letters that are strictly less than n is concerned, it's as if the 3 does not exist where they end up, and so that is this thing. So in other words, if I can recover P of W bar, P of W from P of W bar if I knew its shape, right? So corollary is P of W is determined completely by P of W bar and alpha k W k greater than or equal to 1 or beta k. And you can do the same things for P star and so on. How? Well, so I know that suppose I know that this guy had shape 4, 3, 1, right? And I know that this is P of W. So what should I do? I need to fill it out to this shape 4, 3, 1, and I know that the only numbers I'm missing are 3. So I can recover PW just from PW bar and the green invariant. So I know its shape, I'll just fill those out with n. And proof of the lemma is that, you know, when you insert numbers less than n, they are not really affected by the n's. Where they end up is not affected by the n's. Okay, you need to, you know, sit down and carefully check it perhaps, but so yeah, I am resorting a lot to prove by example in this course, but sometimes it's not very useful to watch someone else prove one of these things. It's better to do it yourself. Okay, so that's that, and now I am ready for the punchline. If P of W, okay, yeah, if W and W prime, or we could, yeah, okay, let's say it like that. If P of W is congruent to P of W prime, then P of W is equal to P of W prime. So the proof is by induction on n. When n equals 1, it's obvious, right? So now when n is larger than 1, let's assume it's true for n minus 1 and so on. So what we have is P of W is congruent to P of W prime. So, this implies that P of W bar is congruent to P of W prime bar. We saw this, right? When you delete the n, the Knuth relations become completely trivial. The Knuth relations involving n become completely trivial. But by induction hypothesis, this means that P of W bar is equal to P of W prime bar, right? And then by this observation, by this corollary. So, it is very simple at the end, but all these steps were needed. And so, what this shows is that every plactic class contains a unique tableau word. It is also true that every plactic class contains a unique dual tableau word. So, you can do the same thing with P star. And the proof is the same. No, it was not. I mean, it need not have been. It was only used because we were too lazy to check K2, and then we said we will do Schutz-Berger involution. But you could check K2 without, right? So what is the moral of the story? The moral of the story is that the plactic monoid, basically canonical representatives for each plactic class, can be taken to be tableau or dual tableau. So, the plactic monoid is really a monoid structure on the set of tableau, or it is a monoid structure on the set of dual tableau, or it is a monoid structure on those pictures that we draw. It's there is a way to see it. It's called jeu de taquin. So this is a very beautiful construction. I'll give you an example of jeu de taquin. So basically, what we want to do is we want to be able to multiply tableau. This is another of Schutz-Berger's creations. So, or how I stopped, how does it go? Stopped fearing and learned to love multiplying tableau. So we have two tableau. Let's just take two tableau. Huh? No. This is Dr. Strangelove, which is certainly American, yeah. So I have this tableau, and I want to multiply it with another tableau. Okay, so this tableau comes first and this one comes second, and I want to find their product. So one way to do this would be to write the word 2 4 1 3 3 2 3 1 1 2 and compute P. Okay, but that seems very boring. What I'll do is I'll play this game called Jeu de Taquin. which is you know that 15 puzzle, right? So you have this square box and there's 16 squares, one of them is vacant and it's all jumbled up and then you need to put them in the order. So it's a sliding game. So that's what jeu d'état is, it's a sliding game. So what I have now is I have this empty space over here and I want to sort of move these squares into these empty spaces. So, so let's try to do that. And at each stage I want to, so at each stage, okay, so let's see, I want to move this square in, let's say I want to move something in here. Okay, slowly I want to fill up all these squares. So I want to move something here. I have a choice, I can either slide this in here or I can slide this in here. Okay, but if I slid this up here, that would be very bad because I would have a 3 and then a 2 and that's not allowed in a tableau, right. So it's better I slide this over here. Now this square has become empty, so I better fix that. So I could either slide this over here or I could slide this over here, but this would be very bad because I'd have a 2 and a 1, so I better slide this over here. And this is empty, but this being empty doesn't really bother me. I mean it's somehow outside this shape. So let's just remove this. Huh? You don't need to, yeah. No, in this case, yeah, I couldn't slide the 1 down because it would violate the 2-1 thing. Okay, now let me pick another square. I could pick this or I could pick this. Which one should I pick? This one. Let's pick this one. So I slide this here, there's really no choice and it doesn't cause any problems. That becomes empty, so I'll slide that here and then I'll slide that here. Okay, so that got rid of that. And then let's see, now I have to slide something in here. Again the 2 wins and now again the 3 wins and this is gone. And now I have 2 choices. Which one should I pick? Huh? Oh, I forgot. Did I do something wrong? 1, 3, 3. Oh. And then it becomes 2, 1, 3. Slide. Sorry, I don't slide things down, I slide things up. Now I understand what Sridhar was saying. You can't slide things down. You have to slide things to the left or up because you're moving. Actually, there's also a Russian notation for tableau where you draw them like this. And then you have to slide things into this corner. So there's this corner here and let's say there's a magnet here and everything has to go there. So now I cannot slide this one, that's never allowed. I have to slide things to the left or up. I'm sorry. So this 3 goes up here and that's fine, right? That's not a problem. Okay, now pick one of these. Upper one again, okay. Boring people. Okay, so then this, okay, so then this comes here and then this comes here. And now I have to move something in here. Can I slide the 2 here? No, I can't, right? I have to slide the 1 up. And now can I slide the 3 here? No, I have to slide the 2 up. And then this is an empty box. This is not good because, so I should slide the 4 to the left. And the last step, so I can't slide this 1 to the left because then I would not have a strictly increasing column. So I slide this 1 up. And I cannot slide this to the left, I have to slide this 2 up, and now I cannot slide this 4 up, I have to slide. It's a deterministic process except that at each stage you have to choose a box. And this is the product of those 2 tableaux that I started with. If you want, we can just check here. So 2, 4, then 1, then 3, then 3, then 2. Oh, what was I doing? Oh man, 4, okay. This requires great powers of concentration. 3, then 1, so that will bump up the 2 will bump up the 3, and the 3 will bump down the 4. It's looking like that. And then another 1, and this one, what was here? 3, right? And that's it. And then there's a 2 which will bump up this thing, and that will come here. And I don't hear any applause, so yeah, it is the same, right? Yeah, okay. So that's a way to work with Tableau directly and multiply them. I won't explain to you right now how this works. But I think you can try to explore this and see what is happening to reading words. So the thing is, whenever you have those things I drew, all the intermediate steps, they are called skew tableau. So they are tableau, except that some boxes, there's a missing piece on the top left, right? It's also a Young diagram, but that's left empty. And you can still talk about the reading word of a skew tableau. And then what you must see is that every time you do a jeu de taquin move, the result is Knuth equivalent to what you had before. So that's why it works. So that's jeu de taquin. Okay, so I think, yeah. So that's a way to work directly with Tableau. You can in fact construct the insertion tableau of any word using jeu de taquin. So if I wanted to construct the insertion tableau of this word, one way to write it without bothering about whether it's a concatenation of 2 tableau or whatever, any word whatsoever, I can write it like this: 2 4 1 3 3 2 3 blah. 1 1 2, and then I have this whole staircase shape that is empty over here, right? And I'll try to play jeu de taquin and get a tableau, and I would indeed get the insertion tableau. And there are 2 ways to do this. I could start clearing out first this, then this, then this, then this, and so on. Or I could start clearing out this, 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 and this, and so on. Yeah, yeah. But I could do this systematically. If I had OCD or something, I would always choose these things in a certain order to move things in first into this box, then into this box, then into this. Or I could maybe first this, then this, then this. And you see, if you do it one way, it corresponds to the steps involved in computing PW. And if you do it the other way, it corresponds to the steps involved in computing P star W. So it also unifies these 2 algorithms of insertion and dual insertion. Okay, so this is all a bit hand wavy, but so Schutzenberger has a big paper on jeu de taquin, but I think it's also discussed in Stanley's in the appendix to Stanley's book, or perhaps is there other good reference for jeu de taquin? Yeah, so Fulton's Young tableau, yeah, Fulton's Young tableau. So it's a very fun way to multiply tableau, and it's also can be used to formulate the Littlewood-Richardson. Yeah, that's what I did here, right? Yeah. That's more or less from the definition. So Sridhar is saying another way to multiply 2 tableaux is just take the reading word of the second tableau and insert it into the reading word of the first tableau. Essentially what he's saying is that you don't have to start inserting over here. You already know that this would be a tableau, and then you just insert. I don't remember where it ended, but yeah, anyway, so. Really? Huh? After 133. So yeah, so this is already a tableau, so you just start with this. and then you start inserting 2, and then you start inserting. Right? That's the normal way. But this is another way, and it has some added sort of symmetry and a very visual nature. Okay, so I think with that I'll stop today. Tomorrow we'll talk about crystal operators on words. The order doesn't matter. Yeah. Yeah, and now you use the fact that there's a unique tableau. The order doesn't matter because there's a unique tableau. Yeah.